A pleasant day to everyone. My name is Terence Serrano. Today, we will present our graduate thesis entitled Solar Lamppost Health Monitoring Using Integrated Sensors and Wireless Network, presented by my group mates Kyle Katimbang, Paul Reyes, and me, Terence Serrano, with our advisors Jennifer De La Cruz and Glenn Magwili.
Introduction. It features technological innovations that uses solar power. It's independent of the utility grid, reduced operation cost, and monitoring of lamp remotely via end devices.
Statement of the problem. Government infrastructures such as solar lamps became casualties of install and forget system. Health status of solar lamp are not monitored so that it is difficult to know when to replace the components that are worn out or broken.
Significance of the study. The study is beneficial to people because it lessens the number of not working solar lamps and enable more mobility to the maintenance of solar lamps.
Objectives. First, to build a prototype that can measure and record the voltage of the battery, voltage of the solar panel, light intensity of the light bulb, and intensity of ambient light. Two, to incorporate power management to the system.
Objective number 3, to establish a connection between lamppost and centralized base station by using a Wi-Fi technology capable of transmitting the collected data to the centralized base station and store it to the database. Objective number 4, to develop a graphical user interface at the web.
The limitations of the study. This research will not include self-maintenance, such as wiping the dust on the solar panel, not affected by outside parameters, such as dust, which affects performance of solar panel, that requires human intervention for maintenance, does not also cover resilient networks.
Methodology. Objective 1, to build a prototype that can measure and record the voltage of the battery, voltage of the solar panel, light intensity of light bulb, and intensity of ambient light.
Conceptual framework. In the input, we need the voltage from the solar panel, light intensity from the bulb, and the light intensity from the environment. After we input these parameters, it is processed. The data gathered from the sensors will be converted to digital signals. The data will be sent from microcontroller to transmit the data to the centralized base station using its Wi-Fi capabilities. And then the centralized base station uploads the data to the cloud, allowing end users to monitor with authenticated accounts. The output displays all data in GUI. It can automatically toggle the state of the bulb by using its sensors, and it allows real-time monitoring of parameters of the system.
List of materials. The materials used in making this project are solar panel, so it can recharge by means of solar energy, solar controller, so it can regulate the voltage coming from the panel, rechargeable battery as its main power source, voltage sensors, light bulb, digital light sensor, microcontroller for transmitting the gathered data to the base station, and SD card at the base station to log the data gathered.
Process flow. The parameters gathered by the sensor are sent to the microcontroller. Then the microcontroller transmits the data to the centralized base station, uploads data to the internet, and the GUI is accessed by the end devices.
Schematic diagram for the transmitting side. From the right side, the figure uh, The solar panel is connected to the solar controller to regulate the voltage from the panel to the battery after the voltage has been regulated. It will charge the battery. Uh, there are two voltage sensors that measures the voltage of solar panel and battery. The voltage sensor connected to the solar panel is connected to an analog digital converter. And the light sensor is also connected to the ADC. Then the ADC sent the converted signals to the microcontroller, and the microcontroller sends the data to the base station.
Schematic diagram for the receiving side. The microcontroller is connected to a PC using USB after the microcontroller receives the data. The data is then stored in the micro SD card.
Objective number 2, to incorporate power management to the system. Power formula. We use the formula power is equals to voltage times current, and the unit is in watt-hour.
After computing the power consumption, we came up with these values. The current of the devices are from the datasheet of the component. In day 1, it can consume 37.29 watt hour.
The capacity of the battery is 84 watt hours.
The prototype can last up to 2 days and 6 hours without charging. Solar panel charging. So the solar panel has a rated power of 10 watts. Assuming that is a sunny day from 9 a.m. to 4 p.m., the charge generated will be 10 watts times 7 hours, which is equivalent to 70 watt hour.
We applied the modem sleep mode in the microcontroller to save energy with modem sleep mode. The total consumption is 37.29 watt hour versus the idle mode that consumes 41.69 watt hour.
Objective 3, to establish a connection between lampposts and centralized base station by using a Wi-Fi technology capable of transmitting the collected data to the centralized base station and store it to the database.
At the data logger in the base station, a text file will be generated and it will contain the parameters coming from the lamp. It will display the battery level, panel voltage, status of the lamp, and battery voltage.
Uh, Objective 4, to develop a graphical user interface at the web.
Here is the graphical user interface at the end devices. It displays the lamp status, lamp state, battery level, and solar voltage.
Results. This is the diagram of the prototype. Lamp A and lamp B transmit the data to the base station, then the base station upload it to the cloud, where end devices can access this anytime.
This is the overview on how we test it. The distance between the lamps and the base station is 12,205 meters.
Conclusion, the parameters gathered states the health status of the component for the batteries according to our related literature. IEEE recommended practice for maintenance, testing, and replacement of valve-regulated lead-acid batteries for stationary applications. If the battery is below 80% of the manufacturer's rating, it needs to be replaced. The design system that monitors the health remotely can view anywhere as long as there is internet. Integration of different components were achieved, and there are acceptable response from the tested sensors.
Recommendation. Additional features in the GUI website. A large deep cycle battery is much recommended for sustaining the power, suggesting to use the latest trend of technology and compatibility of each hardware and software.
That concludes our presentation. Thank you very much for listening.